Thank you, Connor. My name is Sean Quinn. I work at ESA as a young graduate trainee, ESA graduate trainee, working on ESA's first HPC system, Space HPC. My role essentially revolves around the uh, optimization, porting of user applications, system benchmarking, configuration, amongst other things. Firstly, before starting properly, I'd like to apologize for not making it in person. Yesterday, I was stuck at Copenhagen Airport. I don't know if some of you had the chance to look at the news, but there was some German activity in Copenhagen and Oslo, canceling all flights and diverting all flights incoming. So again, sorry for this. Also, I don't know if Connor had the chance to explain that we're currently having some issues with the HPC, where some high priority jobs are currently taking up the queue, so I won't be able to do the demo and the practical session as well, but we'll be sending out, I believe, a video on some of the things that we're planning to do. So if you guys are interested in following that, see how HPC systems are used, etc., then yes. Anything else, Connor, that I'm forgetting, or can I go ahead?
No, you covered pretty much everything. Nice.
Perfect. Sorry, it'd be difficult to answer questions, so if there are questions, just feel free to interrupt me, Connor, and then I can answer them, I suppose. All right, so let's start. So I'll be talking about the addressing of data processing challenges, especially the scaling of computational resources via high-performance computing. So as many of you are aware, there are currently a lot of challenges in EO data analysis. So the increase in EO data sets with satellite data volumes, which are expected to grow tenfold in the coming years, along with the computational intensive processing of this data. So the raw data into actionable insights for usable output is becoming more hard and requires more significant time and resources to do. The accessibility and usability of the output, ensuring that all parties who wish to use the output gets to access and interpret the data correctly, is also a challenge, to name a few. This will mostly focus around the computational intensive processing through the use of high performance computing. So for those who are unaware with the technology, high performance computing, or HPC, is the use of essentially computer systems or very powerful computer systems to solve complex problems that your regular day-to-day system may not be able to handle. So an HPC system is essentially what some would call supercomputers, which is essentially made of a cluster of computers made up of many individual parts, even smaller computers, some would say, that work together as they're interlinked with very, very fast network to be able to share data quickly and communicate to handle these big tasks. So instead of relying on one very powerful computer, an HPC system would use a lot of computers at once, which creates teamwork and lets them tackle bigger tasks that you won't necessarily be able to do, or they won't be able to achieve by themselves. This is achieved through parallel processing, which is essentially the splitting of these big tasks into the smaller parts that are solved simultaneously across these computers, which is essentially speeding up the process of calculations dramatically. And then you have more specialized hardware. So HPC systems use your day-to-day components like CPUs and GPUs, but at a much larger scale. So for example, my computer would have 36 cores on its CPU. On an HPC system, you can expect numbers like 192 cores on a single CPU, etc. Obviously, you also have much more powerful graphical processing units, AI processing units. You have very fast storage access, as well as much larger storage. And HPC is used in a wide variety of fields and scientific research, engineering, weather prediction, finance, more. Again, it enables for quick solutions to complex problems that would take years on normal computers to do. So as I said, HPC uses specialized hardware, So in case some of you are unfamiliar, you have your CPUs and your GPUs. CPUs can handle a wide variety of tasks that are more complex, that require more instructions, a lot of IO-based interactions, etc. It has also a very high, fine precision on its floating point operations. Unlike GPUs, on the other spectrum of processing tools, you have a higher level of parallelism, so they have a lot of threads that aren't necessarily the smartest threads. So for example, you'd be able to do tasks such as AI, ML, training, data mining, high-res graphic rendering, image processing, etc. But you won't be able to do parallel I/O with a GPU. They often rely on CPUs for the provision of instructions, as well as message passing, etc. They're a lot less flexible for some tasks, but they're very powerful for simple calculation-based tasks. That's why we rely on them for example, AI ML. Another aspect that I mentioned that HPC heavily relies on is parallel execution. So for example, let's say that a task takes X hours, let's say 80 hours in this case. On a single process, can you see my mouse? I'm not sure you can. Uh, I'm going to assume no, but so this red processor here, let's say is single processor, it'll take 80 hours to do a simulation. Now, if we introduce four more or three more processors, what's essentially going to happen with a word divide is we can decouple this task into two tasks, for example, and go down in execution time as we divide the workload amongst all the processes, essentially running down to a quarter of the time to do this simulation task, image processing, whatever it may be. Now, I wish that it was this simple. This is the ideal theoretical case for what we call speed up, which is essentially how much faster you are in your application in terms of either increasing your workload or increasing the number of hardware you're using. This is the ideal case where you have a one-to-one mapping, but in reality, things are more like this, um, where essentially communication between all processes is required. So let's say that everyone's given the first part of the simulation. What essentially is going to happen at some point is everyone's going to need to be aware of where we are in the simulation. So this introduces overhead in the form of communication between processors. Once this is introduced, different processors will be at different stages of the simulation, introducing wait time for some, which is a form of load imbalance and therefore inefficient run. But this is very common. It will always happen in certain applications. In addition to this, another aspect that is considered is storage. So for some applications, mostly in Earth observation, for example, the data sets are extremely large. So we might not be able to hold all of that data that we're using in the resources used for the application. So what you're going to start doing is transfer from the memory, so the RAM, to your system's main storage. And this will introduce more overhead, thus more time because you're writing and saving files of somewhere else, which is not close to your RAM memory, which will be on premise with the rest of your resources. Now, if this didn't sound complicated enough, there are also a lot of challenges with using HPC systems. They're not an out-of-the-box solution. In terms of usability, they're often command line interface based. So it'd be with the terminal interactions, you'd have to use commands, etc. To add to this complexity, most systems are Linux-based environments, so you do need a certain degree of familiarity with Linux environments. Um, in addition to this, you also have schedulers, module-based environments, a lot of things to consider, but I can promise you that once you're familiar with this, you do feel like a tech whiz at some point. As high as the learning curve may be, it does plateau at some point. Another challenge that's currently being faced is the transfer of large data sets. It's an ongoing challenge. We have applications such as Globus and fast file transfers or parallel file transfer based applications to try to solve this. but at the end, you're still stuck at the bandwidth that's available on your internet. In terms of the application and environment, as I said, this is not an out-of-the-box solution. So whilst, for example, on cloud systems, you would be porting an application in the form of an image or a container-based tool. In HPC systems, quite often you require the porting of an application environment, which can be tricky if not out of the box. So you might have to do a native Conda environment installation, even installing on Conda, you on Python, etc. for Python-based. If this is more to the metal, so compiled languages like C, C++, Fortran, the dependencies also come with. So the software stack on an HPC system might, for example, might not necessarily be present. So it is your job as a user, maybe with the help of a sysadmin, to port your dependencies and application based on the system's specifications. Another thing to consider is that not all applications are parallel. So some applications might just be serial, like the example I gave earlier, where essentially you had a single execution by a single process. Not all applications are able to rely on all the resources, and this may require you to get your hands dirty and use parallel frameworks such as OpenMP, MPI, that blue logo over there, or for our GPU-based application, CUDA or Roxyam. In addition to this, if you want an effective use of HPC system, a certain familiarity of the intersection between hardware and software is still required. So you'd want to be able to say how many resources you want to prevent bottlenecks. You'd want to be able to specify how you allocate those resources based on how you divide the work. So an example of this would be, this is essentially the workflow of a user for an HPC application. You as a user would go to your login node, where that's where you handle your file system, you specify your paths, your directories, etc., of where the data is located, where you want the outputs to be your environment variables, in which then after you define a job submission script to then forward to what we call a batch scheduler. So essentially, in your job, you'll specify the number of resources you want, such as I want 15 CPUs, I want 15 nodes with 4 CPUs each, something like this. I want this much memory. You forward that script to the batch scheduler, which will then look at the current jobs that are allocated, and if the resources are available, it'll map a place in time for your job to be executed. Part of what I wanted to do for this session was to do a more hands-on, show you a demonstration of the process of submitting a script, but I wasn't necessarily able to do this due to the constraints I currently have with the system. But for example, the hands-on session, we were planning on doing a pen sharpening application, which is the process of merging high-resolution panchromatic and low-resolution multispectral imagery to create a single high-resolution color image. So you can see it on the left here, where we have 4 bands of 6-meter resolution and then 1 band of 1.5-meter resolution. We'd be combining them together to create this 4-band 1.5-meter resolution image on the right. Essentially, we'd be demonstrating how to effectively use an HPC through parallelization, so splitting a big problem into smaller ones. So here, for example, we have that image on the left of 1,000 by 1,000 pixel through the use of libraries such as Dask, the Orpho toolbox, and a custom code that we developed. What we're going to do was parallelize this into different grids, which would be allocated to different hardware components. What it would have been looked like, what that would have looked like is the submission script here, in which, for example, on the first line, we essentially select, or we can see that this is a job script, which is divided into 3 parts. The first part is the resource specification. The first line, which starts with hashtag or PBS, we select 3 nodes with 192 cores each and 192 procs per node. The MPI procs is essentially an instance of an application, in which case we're mapping 1 instance by 1 core. We're then requesting 30 minutes of wall time on the CPU queue, a queue being a list of resources. So for example, in our system, we have a CPU queue for all the CPU nodes, a GPU queue for all the GPU nodes. And then afterwards, I'm giving it a name, so workjob or slash job. And then we have our environments. So here we're loading some dependencies that are with parallelization, Cray and Pitch, which is the message passing framework developed by HPE, the Cray parallel, another Cray parallel dependency, as well as Cray PE Genoa, which is specific to our architecture. So these are small things that help with optimization and enable parallelization that we specify. Afterwards, we source a Conda environment, which we activate, which holds GDAP. And then we have our execution, which is npi run, the npi command for executing an application in parallel. And then we specify the number of processors through -n, 192. We'll just specify 192 instance of our application, and then it'll be your basic Python executable command. As for GPUs, we wanted to do an example of a resolution improvement where we go from a 10-meter resolution to a 5-meter resolution through the use of an AI model. In this case, quite similar to our CPU request or job script, where we select 4 nodes with 4 GPUs each. We do specify CPUs, as GPUs do rely on CPUs in this case. We request 650 gigabytes of memory, which is RAM in this case, with a wall time of 20 minutes on the GPU node. Then we do our environment, where we specify some sockets, affinities, etc., before executing a Python command. Now this, again, as I said, would have been demonstrated, etc. I can try, I believe, to at least show you what a more realistic, so please let me just share my screen, what a more realistic script would look like. So currently I am on the Space HPC, ESA's own HPC system. This is one of my old projects. So if I go to HPL, you can see all my outputs here. I'm just going to show you real quick what a more realistic expectations in terms of job scripts would be. Again, here I specify my resources, here more environment, except here I do more affinities where I specify, this is what I meant earlier by some knowledge in terms of the interaction between hardware and software is required for very efficient execution would be needed, is to an example of here where I specify a lot of things which I will not get into, but essentially just some memory spacing allocation, etc., sockets. And this would be my command where even again, I have more optimizations, etc. It does not need to go in this much depth, but it is helpful if you want to reduce your runtime, for example, from 4 hours to 2 hours. You can expect this kind of level for very high data sets and intensive workloads. And then if you'd want to submit, it'd be through this command. This is, I believe, on one node, as this is all I can do at the moment. But after I submit this job, essentially it'd be on the node or on the queue list, as shown here. And then it's on with some other jobs. Something I said was module environments. So I'll show you a little bit once I have a bit of time. This is the current Linux module tool. So in an HPC system, you'll have a set of modules which essentially are software compilers, etc., that you require dependencies for your application. Familiarity with this is required to port your application. So as you can see, it's not necessarily out of the box. Here we have some GPU, NVIDIA-based stuff, more general compiler-based stuff here, etc. So I'm not going to bore you too much with this. I'll move on. Am I still presenting?
No, now we just see your face.
Ah.
Just was a bad thing.
So let me just, okay, where were we? Yes, nope, not there. Here. Now, as I said, this isn't necessarily intuitive for everyone, so there are works being done. There are some people, sorry?
Yeah, mine is normal now.
Say that again. Sorry, I cannot hear.
You can continue. It's just
Ah, okay. All right. Perfect. So there's some people, for example, at the Supercomputing Center Cineca of Italy, ECMWF, DKRZ, who are developing hybrid cloud HPC platforms to make it easier for people to use these systems. Also because they're varying use cases. So, I should have gotten a bottle of water. So in this case, let's go back to the EO data challenge, where we have the exponential growth of data volume, the variety and complexity of that data, again, the distribution of that data to user access, but the computational intensive processing. So that's again the focus here. In terms of what the cloud and HPC provide, cloud gives essentially an on-demand resource that's very easy to expand. So things like AWS, Azure, Google, etc., give you that platform in which if you don't have enough resources, you can easily scale it. However, unlike HPC, the optimization in large-scale compute might not necessarily be there. So what they're trying to do is combine it. So for example, for EO data simulation into models, you'd rely on HPC systems to make that quick, whilst on-demand pre-processing on EO data might be more cloud. So in this example, what we'd want in this merger would be a global, for example, the global deforestation of mapping using Sentinel-2 and Landsat data over, let's say, 10 years, could essentially rely on cloud for the regional analysis, so more wider span, whilst a more refined area like a continental processing would be on the HPC part of this platform. So essentially enabling users from a cloud platform to do this on the fly, either on the HPC or the cloud. Again, this is essentially the workflows that you're working with. In HPC, the user goes into the login nodes and makes a request through Slurm, which then goes to the compute nodes, which interacts with the storage. On cloud, what you have is more the user interacts with some sort of platform web interface, which then makes cloud-based APIs, which behind the scenes access whatever technologies, hardware it needs. There's a lot of similarities between the two in the sense that they both rely on parallel processing, they both allow for virtualization, leverage on the concepts of distributed systems, provide resource scheduling, etc., offer user interfaces and jobs, but they're a lot more different than people necessarily expect, in which the purpose are different. So whilst in cloud you have more of a scalable solution for IT services, in HPC systems you have more of a tightly coupled computational system made for for high performance solutions. In terms of infrastructure, one's more centralized whilst and dedicated, whilst the other is virtualized. The performance is higher on higher on HPC systems with higher speeds, whilst it varies on cloud because you might not necessarily care about these things. You have other things like resource management, scalability, which changes. It's quite scalable on cloud, but in HPC, you're given what you're given in terms of the limitations of the system. You have different cost models for each. Software environment is a big one. Again, the whole aspect of porting your own application versus having solutions that are already existing through images, containers, etc. The data locality is quite different between both, whilst the cloud has essentially storage that's not required next to be coupled with the compute. HPC systems require the data to be hands-on with the compute resources allocated for the job. Security and compliance are something else, but is also a concern for a lot. So why we need it is the different strength for different needs, something I specified before. Whilst HPC is more on performance, the cloud gives you that flexible API-driven solution. Hybrid workflows that are becoming more popular amongst applications have varying pipelines. For example, the HPC could focus on the model training or the very high compute stuff, whilst the cloud could give you a solution for the analytics, virtualization, etc. But yeah, and then after that, it's the compliance, whilst HPC are on-premise. You're sure that they're more secured, controlled, they have policies, and cloud systems are hosted by another entity. But they do allow for rapid innovation, so restructuring, implementation of new aspects, etc., in your infrastructure. Essentially, ideally, what would be perfect for you as a user would essentially be the use of developers and scientists to create this platform that relies on reusable components, tools, services that has previously been defined as required for an application, but that leverages on HPC and cloud together. Now, in terms of what we have here at ESA, we have the Space HPC system, which is a technology demonstrator purposed for research and development teams that focus on the exploration or the improvement of the European space industry. It was built as a modular system in ESA Esrin in Italy, using what at the time was essentially the best hardware available. In terms of use cases, the system's made and designed for varying things that the agency focuses on, from simulations to AI workloads, data processing for Earth observation, and more. What this looks like is, I don't know how big this is for you guys, but essentially quite modular partitions that have CPUs and GPUs. So we have 34,000 CPU cores, 124 H100 GPUs, 3.6 petabytes of storage, 156 terabytes of RAM, and two dual InfiniBand high-speed networks for one dedicated for data access and one for communication-based communications. If some of you are familiar with the top 500, it's essentially a list of all the systems in the world, or supercomputers in the world. The space HPC system managed to reach the 261st spot in the top 500 and 59th in the green 500, which is more of a renewable point of view on HPC systems, seeing how efficient we are, what our flop rates or floating point operations per second is in retrospect to our energy usage. How it benefits the industry is essentially what we planned is to provide access, easy and fast access to SMEs for innovation, as well as internal and partnered researchers to the system. This comes at no cost until the end of 2025, has flexible scalability on what resources we can give, etc. It's purposed for R&D, as I said. It's accessible. We're trying to implement a light application process. It's currently online. I don't know if the link is here, but I'll put it in the chat for later. So you do a quick request of why you need it, for how long, etc., and then we'll hop you on once things are ready. In terms of technology, as I said, we have a general partitions made of CPU nodes, an AR partition made of GPU nodes, an accelerated partition, which is a mix of more performant GPUs, the high-speed network that I mentioned before, and a guaranteed data locality storage. So the project or the system's been installed in early September. Through then, we had interactions with a lot of internal ESA users through the form of early access, sample system, test phase, and we're currently in our ramp-up phase. We've had the chance to work not only in Earth observation, but other things such as space exploration, rocket part research, etc. Everyone's been giving us feedback, so we're trying to tailor our environment to your needs. An example use case we have here is space weather modeling, in which one of our users had to do essentially simulation of the sun's corona. I'm not going to get too much into that as that's really not my field. But essentially the outcomes were through their old system, which was a virtual machine with 8 CPUs. It took around 2 days to simulate, around 6 hours of simulation time. We managed to reduce that to 10 hours whilst we were on our sample system, And on our system, we managed to reduce the compute time to 7 minutes. So from 2 days to 7 minutes, the virtual machine being a somewhat more realistic representation of what your day-to-day computer would look like. So the user managed to get some significant output from this. Unfortunately, this is all I have with the constraints. If you do have any questions, please let me know.